Good afternoon, everyone. I am super excited to see everybody. I am going to get us started. My name is Sarah Vanderwerp. I'm the MDE Academic Standards Specialist, and we are doing a webinar series on all 7 anchor standards in the new 2022 math standards that will be fully implemented in the 2027-28 school year. And these videos are being recorded and will be up on the MCTM YouTube channel sometime. There are 5 of the 8 webinars already posted there. So if you Google MCTM YouTube, you'll be able to find the webinar series. So today we're super lucky to have not me presenting to you, but one of my colleagues here at the Minnesota Department of Education, Amy Nolte. Amy Nolte is one of the 2 MDE math assessment specialists. Her colleague, Mike Huberty, is in the chat. And I'll be saving the chat so Amy can, if she doesn't get to your questions during this meeting, she can get back to you at some point. And if you're watching this webinar, leave your questions in the chat to the video, and we would love for you. We'll try and follow up and check those occasionally. So Amy, without further ado, I'll turn it over to you.
Thank you, Sarah. So good afternoon, everyone, and welcome to Anchor Standard 6, Equivalence and Relational Thinking. Sarah did a wonderful introduction for me. I'm Amy Nolte. I am one of 2 mathematics assessment specialists at the Minnesota Department of Education. I'm really excited to talk about equivalence and relational thinking because it's one of my favorite ways to play with mathematical concepts, as well as just math in general. So we're going to spend some time today doing some math, as well as making and creating some common understandings around the shifts from previous year's benchmarks to the 2022 benchmarks, and then what it means in your classroom. Just as a reminder, the resources for all 8 sessions are found at this bit.ly. Sarah also linked it in the chat, and I do believe if you're watching the recording, you will find it in the description below. I'll give you a couple seconds if you'd like to open that up. So really briefly, if you've watched one of these before, this will not be new to you, but just in case, the 2022 math standards for Minnesota have 7 anchor standards that are written like K-12 progressions. The standards are also split into 3 strands. So Anchor Standard 6 is in this 3rd strand. Anchor Standard 6 is very closely tied to its strand friends, 5 and 7. Really, we're going to be focusing a lot on representations of numbers, transforming numbers, and ways of thinking. In order to do that, we're going to start off the day by counting. So at MCTM this year, I watched Christopher Danielson presenting this, and I, of course, was sitting in the way back and took the fastest photo I could possibly do, and it is so blurry, so I apologize for that. But he presented and really talked about counting and it in its middle grades. So counting is explicitly named in the early grades in Anchor Standard 5, but we're really going to bundle the ideas of Anchor Standard 5 and Anchor Standard 6 together because they are so interconnected. Also, counting creates a really strong foundation and helps create very accessible mathematical experiences, no matter the grade level. So I took this picture. It's blurry. I've thought about reaching out to Christopher and asking, can I have a copy of your picture from your new book? But I thought, why not just recreate one myself? So I went out to my backyard and found some beautiful flowers. And we're going to take a few moments and count the number of petals for all the flowers. Now, as a scaffold, because I know that this image on the right of these wonderful lilies, it's kind of hard to discern the number of petals. I will tell you that the number of petals on each yellow flower is 5, and each of the orange flowers has 6 petals. So as we count all of the petals, I want you to pay attention to how you count them and be ready to share your method. If you get 1, see if you can find a few different ways that you can count it as well. So in the classroom, I wouldn't necessarily tell students to write expressions for these, but for the purpose of our webinar today, I'd love if you could write some expressions that show how you counted those number of petals. If you're watching the recording, pause the video and write down some different ways to count the number petals of all. So go ahead and take a few minutes.
We're getting some in the chat. We've got a 5
Oh,
times.
don't share them yet, Mike. Don't share them yet.
Right there. Okay.
Even though everyone can see them. One thing I noticed that's interesting is some people are just giving it expressions and some people are giving equations that include the total. That's really cool. Okay, so I saw a lot of things and you might see something similar here too. What I would do as a teacher is as my students shared how they counted it, because a lot of them might not go to expressions right away, I would write the expression as they describe it. So I would ask, how do you count it? And I might have some students, which none of you did this, but that's okay, that might add 10 plus 10 plus 10 plus 12 plus 12 plus 12. I want to make sure that the expression matches the picture. We want to be able to visualize both of it. And I saw this a couple of times, 6 times 5 plus 6. The way that I see that is a 5 plus a 6, and another group of 5 plus 6, and another group of 5 plus 6, 6 times. As Sarah put in the chat, the distributive property. Another student might do 15 plus 15 plus 18 plus 18. I saw this one a lot in the chat. 6 groups of 5 plus 6 groups of 6. Or as simple as 30 plus 6. I don't know what student's just going to know that that's 30 off the top of their head, but you never know. It's their choice. They can do it however they want. And a lot of other ways. In fact, I even saw someone use a variable in the chat, 5a plus 6b. There are different levels of sophistication that students can use when they're doing this. Sorry, sometimes I'm reading the chat and I'm getting a little distracted. Students can use different levels of sophistication. They can count each one, 5 plus 5 plus 5, which might be a lower grades thing, up to using exponents or variables. So another thing to think about is when we present a problem like this, so we start kind of at a ground level where students can access it no matter their knowledge. We can think about what we might want to push students to. So there might be a benchmark or a concept that we really want them to do. So I might want students to use 2 different operations to write an equivalent expression. So this one won't work, but maybe multiplication and addition will. So if I wanted to focus on equivalence, I might pull out 2 students' expressions and show, how are they the same? How are they different? How can we relate them? Or how might we expand it and use factoring? How can we compose and decompose this picture to look in different ways? Of course, always talking about the meaning of the equal sign. I can also start thinking relationally about this, and we haven't talked about relational thinking yet. We will in a little bit, but I can think about it relationally, or thinking about unknowns and variables. And we really want to think, how are these expressions connected? We're going to do another activity in just a moment where we're really going to build on this relational thinking, which you can kind of see here, but we haven't quite touched on. So we're going to start with some true or false equations. These are really intentionally planned, where I want you all to use reasoning instead of calculating each side of the equal sign to solve them efficiently. So, first one. Go ahead and type in the chat if this is a true or false and what your thinking is. I'm seeing a lot of comments that are similar to what I expected you to say. True, because subtracting 600 and 600 is 0, and the 10s and the 1s are the same. I'm also seeing comments about them being the same distance apart. How about this one? 300 times 72 is the same value as 3 times 720. True or false? I'm seeing a lot of the same thing that I thought you would say. The multiplying by 10 changed from the 30 to the 72, so it's the same amount. I see people saying things like 3 times 10 times 72 is equal to 3 times 72 times 10. Or someone even talked about using the associative property to help it out. What about 52 plus 29 equals 54 plus 27? True or false? And how do you know? Just remember, you're not allowed to actually add either side. You have to think relationally. As you're writing your comments, I want to address, Sarah just wrote, these true false questions are a great routine for Anchor Standard 6. I agree, they are a great routine, and they're actually written in the benchmarks. So students actually have to solve true or false equations as part of the benchmark. Oh, there's a lot of really interesting thinking for this third one that some of them I didn't even expect. So some people are saying the 2 you added to get 54 balances the 2 you subtracted from 29. Or similarly, 52 is 2 less than 54, and 29 is 2 more than 27. And other people said 50 plus 20 is 70, and both 2 and 9 and 4 and 7 are 11. And some broke it down even in oh my gosh, a lot of different ways. I predicted a similar way to the first ways I've talked about. So you add 2 to 52. So to keep it the same value, you had to take 2 away from 29 to keep that balance. And our last one, maybe, there we go. 82 divided by 64 is the same value as 41 divided by 32. True or false? And what are you thinking about it? I am loving all the vocabulary that's coming out in this one. This one I intentionally made a little bit harder because it doesn't divide out evenly, but you can know that it's equal because some people thought of them as fractions and think that they're equivalent fractions, it's just divided by 2. Some people talked about the balance staying the same, about doubling and halving, and someone even talked about it looking at ratios. So equivalent ratios instead of just equivalent fractions. I also thought about it like fractions and division are related. So it's like an equivalent fraction. I just want to note that none of these required you to find the value on either side, but they all simply required you to think relationally. So when we think about Anchor Standard 6, the counting and true-false equation activities are just a couple of ways to really get at the heart of this anchor standard. We want to be using those concepts and properties of equivalence and relational thinking to represent and compare numerical expressions, proportional relationships, algebraic expressions, and equations. So as we kind of shift from our old standards to our new ones, I wanted to just really briefly talk about and give you some questions to dive deeper into the shifts of these benchmarks. We don't have time today to really dive deeply into this for all the grade levels. And I have a document called Similarities and Shifts, or I think it's Benchmark Supplement that I gave you if you have time to take and dive into this, whether it's with PLCs or even on your own. And it also includes not only the summary that I'm going to show you, but also a list of all of the 2022 benchmarks for Anchored Standard 6 by grade level. So really quickly, there are many things that are going to be the same from the 2007 benchmarks to our 2022 benchmarks. The things that are shifting a little bit are really just a new emphasis. Primarily, we're going to be more emphasizing what is the meaning of that equal sign, looking at the relationships between expressions, forms of expressions, models, really a higher focus on structure, really MP6, and making conjectures and justifications, which is starting in grade 2, where students are justifying their understanding of equations and expressions. And it's a much more cohesive progression of equivalence to support algebraic thinking, kindergarten through grade 12. So if you look, I really noticed structure is going to show up in every single grade level. That is going to be a very important emphasis, as well as looking at equivalent forms of these relationships. Primarily today, we're going to focus on these 2 questions. And really question 1 is kind of 2 questions, but I'm going to call them 2 questions. Equivalence has been in our benchmarks previously. Because relational thinking is a new term for the 2022 standards, that's going to be the primary focus of today, but we'll still be talking about equivalence throughout. So what is relational thinking? Why is it important? And how might you promote that thinking in your classroom? So again, in order to think, we're going to talk a little bit about what these words mean. And in order to think relationally, we have to have a strong understanding of equivalence. We need to know that equivalence is a true relationship between values, that the equal sign is a relational symbol. Oftentimes students misunderstand what the equal sign actually means, and that equivalence really demands us to read and encode the structure of equations. I love this polypad video because it really exemplifies equivalence. When the relationship is true on both sides of the equal sign, the scale will be balanced. As they manipulate the equation and the balance is adjusting, they're really reading and encoding the structure of that equation that they're manipulating. It's also just really fun to play with. I'm just going to say that. As we get into relational thinking, I want to talk a little bit about the history of it. So in 1976, Richard Skemp released an article that was published in Mathematics Teaching. It is a very, very detailed explanation of relational understanding versus instrumental understanding. It talks about the advantages and disadvantages of both types of understanding, as well as some thoughts about how maybe we all aren't defining mathematics the same way, so that might be a part of why there's some differences in understanding and how our students are performing in the classroom. It is also linked in the resources. So instead of reading the whole thing right now, I want to show you my favorite visual, because I love visuals, about this. So this image is from David Weiss, and it really summarizes instrumental versus relational thinking well. So instrumental thinking really shows these isolated pieces of knowledge, and it does have its purpose in certain areas. Relational thinking is really about building these robust connections. There might be some more isolated pieces off in the distance and other things that are more tightly connected, but the ideas really build off one another. Skemp put it this way: students who are taught instrumental understanding come to see mathematics as isolated pieces of knowledge. They are expected to remember procedures for each and every concept and skill. Each new skill requires a new set of procedures. However, those who are taught relational understanding make connections between and within concepts and skills. Those with relational understanding can learn new concepts easier, retain previous concepts, and are able to deviate from formulas and rules given different problems easier because of the connections they have made. There are a lot of components that come together when we think relationally. The work students are doing in the other anchor standards, especially its kind of sister anchor standards in the same strand, its anchor standard friends, as well as those math practices that Sarah has done a lot of webinars about, and these benchmark contexts all support relational thinking. Relational thinking is not something done on its own. It's done in connection with many, many other things. It lives up to its name. So a really drafty, unofficial definition that I've been using is this. Relational thinking is the ability to reason about mathematical relationships without always relying on computation. It involves recognizing patterns, using the properties of operations, and understanding the structure of expressions to make judgments, justify solutions, and solve problems more flexibly and efficiently. A lot of these highlighted words are also found in all the other anchor standards and in their language because it's so connected. So mathematicians have described relational thinking in a few different ways. There's tons of articles about relational thinking all over the internet. And I've pulled out kind of my 4 favorite kind of definitions. And like I said, I love visuals. So I'm going to give you some of those visuals today. The first one, relational thinking is a bridge between arithmetic and algebra. Or I could think about relational thinking integrating arithmetic and algebra. Or a mindful application of place value and the properties of number, operations, and equality when solving mathematical problems. And finally, the center of algebraic reasoning is relational thinking, which involves coordinating quantities in mathematical expressions, often without calculation, using flexible reasoning about quantities and converting mathematical expressions into equivalence. I just want you to notice how relational thinking is inextricably tied to algebra and algebraic thinking. And another connection is Math Practice 7 it's all about structure and transforming problems into simpler things. Again, Math Practice 7, Anchor Standard 6, they are so strongly related. So let's talk about what this might look like in your classroom and why it's important. So here's a classic problem. 8 plus 4 equals box plus 5. The most common student responses for this are 7, 12, 17, and the answer, it's both 12 and 17. When they gave this to 5th and 6th grade students, this is the percentage of students who answered these. So 2% of students got the correct answer of 7. 76% of students said 12. So if you take a few moments, you'll see students who said 12 probably think that the equal sign just means the answer comes next. So 8 plus 4, oh, that's 12. We had another really high percentage of students that said 17. As someone who looks at assessments all day and helps figure out where do students commonly make mistakes, students really like to just add all the numbers they see. And that makes sense. 20% of students added all the numbers they saw. And another 2% thought, maybe it's both 12 and 17 because 8 and 4 is 12. And if I add all three, it's 17. Sarah told me when I was talking to her about this problem that she said that a quarter to a third of her 9th graders would also say 12. So this problem doesn't go away magically after grades 5 and 6. Students really struggle with the meaning of what this equal sign means. So what we really want to do is build the meaning of arithmetic as well as algebraic thinking at the same time. We want students to flexibly solve problems using relational strategies. So in the classroom, we want to make sure we use equality with properties, relationships, and/or structure. We can't do it all at once to find equivalence and solve problems. So equality, again, we want to talk about it maintaining a balance on both sides of the equal sign, that it's used as a relational symbol. Equations, remember, can be true or false. So it might look like you can write it, but it won't be balanced. We also want to talk about the properties. These properties of operations are so important. And not just that they know the names of the properties, like, oh, this is the associate, but they know how to use them. And then they can use them flexibly and creatively to create equivalent expressions. So a couple of things that we know work really well to help understand the meaning of the equal sign. Students need to be able to read and use it as a balance. So that's really important in the language that we use. So instead of just equals, we also might want to use is the same amount as, or is the same value as. So that really helps them understand that balance part of it. We want them to see the equal sign in a variety of ways. So most textbooks will put it in a very, a value, an operation of value equals one other thing. But that kind of helps promote that misunderstanding that of what an equal sign is. So students need to see things like 6 equals 6. The amount of students I've had that says that this is false, that you can't have 6 equals 6, is so high. They just don't see it that way. Or 6 equals 5 plus 1. Again, I hear all the time that it's impossible. Or even something as 2 plus 4 equals 2 plus 4. And they still do need to see it in the classic way. We also want to reserve that equal sign for use as a relationship. So again, strings of calculations can really reinforce the misunderstanding of the equal sign, or sometimes even showing it between pictures. We really want to use it as a relationship between values. When we look at relationship and structure, there's a few strategies that students naturally use if we give them problems that really reinforce those strategies. So one of them is the compensation strategy. I heard someone mention that in the chat. Well, I didn't hear. I read someone mention it in the chat before with a similar problem. And again, these strategies, a lot of times I show them with kind of earlier grade levels, but they can be used with variables all the way up through high school. It's all algebraic thinking. So we have a compensation strategy. Take a few seconds and think, and it shouldn't take long, just take a few seconds and think, what might I put for the missing values? And my little square didn't show here. So just imagine a little square above this 8. We have adding and subtracting a group. We have some place value strategies. Again, we've already solved this problem, but people named that explicitly when we did this problem, that they were working on place value. We have constant difference. I always like to compare because some strategies work for addition, but they don't work the same for subtraction. But like, I love this because I could teach kids, and it is important that kids know how to regroup. But this problem is so much easier to solve if I just add a fourth to both. And then doubling and halving, which is one thing we also looked at earlier. I want to give you all just a few minutes to think about, to write 1 or 2 problems, to choose a strategy or choose 2 strategy, and share some problems that you could use, even if it's not in your classroom, but that you could use with students, no matter what level they're at, that could get at some of these strategies. So I'll give you a few minutes to maybe share some problems that you could write for some of these strategies. Oh, which reminds me, if you're watching this, the recording, take some time to pause and write down a few problems, and you can share them in the comments below. I see Charlotte shared one that has exponents, looking at some of those higher grade levels. And I use boxes here because it's accessible for all grades, but also we could always use variables for the upper grade levels. You could also use boxes in upper grade levels too. I'm going to move forward, but I will say anything that you share, we're going to collect it in the chat. And it's nice to have groups of problems that you can use in your classroom to really pull out some of these different strategies. So please share so that we can share it out with other Minnesota educators, or I guess anyone on the internet who wants to watch a webinar. Also, one thing I forgot to share. Sarah, coming up later this week, there is a big Anchor Standard 5 training. And one of the things is she made this really cool models and strategies document. And it's really in its initial stages, but it is a really cool way to look at your grade level and see what strategies and models might they be using. These are in there. So we didn't even develop it together. They're just a thing that students use. So something to keep in mind. That is in the resources as well. So also to help you out. Oh, I forgot. Did I forget? Come on. My computer is frozen. There we go. I kind of put together some of these across grade band things to help you focus on what you might want to work on depending on which grade level you teach. So for K2, our focus on content is going to be place value, addition, and subtraction. And again, a few ways of how to do it. These are all from the benchmarks. We can use true, false, which we've already had experience with, open number sentences and unknowns, which again, we just experienced, and making conjectures. Again, we've all been doing that this whole time. So it might be in kindergarten, just decomposing a number and seeing all the different ways that values are equivalent to 8 for this example. Like we've already done, adding and subtracting using true, false. A lot of the ones I showed only have two values, just one operation on each side, but you can expand it, right? We can use a lot of different ways. It could just be one. Students commonly will subtract the 6 minus 4. I know I've only been doing true ones, but we do need to have some false ones in there that are common errors that students might make. And then again, doing the unknowns. A lot of times, so unknowns are introduced in grade 1. So students start working with unknowns really early. So that algebraic thinking is really being built up. For 3-5, our focus is going to be for content. Again, place value, addition and subtraction. It's going to expand a little bit into rational numbers, starting with multiplication and division, and having expressions with multiple different operations. And we're going to be using the same way in how to do it. True, false, open number sentence, and unknowns. I love these ones for subtraction. It does not make sense for me to slash and borrow and redistribute for when I have all these zeros. I'd rather make it a much easier number. Again, they're using multiplication and division and using multiple operations. One thing I really want to point out is I intentionally used multiple operations instead of order of operations, although that is introduced in grade 5. Because I don't want us, it's really important in relational thinking that when we do order of operations, at times we do want to definitely get to getting that singular value, but we want to be open to decomposing and composing from that. So for example, in this one, students might do what's in the parentheses first, following order of operations, but they also have the choice to be flexible and distribute if that's for some reason what they want to do. So it's important that they get a variety of experiences using multiple operations in a lot of different ways, not just simplifying. When we start looking at secondary, again, true, false, conjectures, multiple representations, and decomposing and composing. This is where we have all the operations. We get into ratios and proportions. By the way, in summer 2026, There's going to be a more extended training on this, so it is coming. We're talking still about equivalence and solving. Oopsies. So similar to things that we've done, we can use unknowns or we can use boxes. When we talk about equivalence, we really want them thinking about about equivalence in a lot of new ways. So instead of just solving for A, thinking about what do you know about it? Or writing as many expressions that are equivalent to a given expression that they can. This will also help them really learn about combining like terms and other algebraic things. For ratios and proportions, I didn't give very explicit things because the most important thing is that they're using a lot of different representations and they're comparing and justifying those representations. So again, referencing that strategies and models that Sarah is going to be talking about more this week. There are a lot of different representations that really help students understand ratios and proportions. And it's really important that those aren't ever just an isolated thing, that they know that they can use different ones based off the problem. And again, we're getting much more sophisticated as we're getting up through these grade levels. In high school, quadratics become really important. We're talking about polynomials and really equivalence and comparisons across those multiple forms and models. We really want to use those previous knowledge from structure and the properties of operations to be very, very flexible. We're going to be looking at quadratics. We're going to be talking about comparing and equivalence. And again, polynomials. Using different models, explaining and justifying why things work without expanding. Really, we want students using and describing the relationship between the left side and the right side of that equation or inequality. So when we're thinking relationally, we want students to look for those relationships and structures. So we want to explicitly connect to them arithmetic and algebra. That's what relational thinking is. We want to make sure that students pause, that we model pausing and thinking about, is there a structure or a property that might make this problem easier before I just jump in? We want to encourage flexibility, decomposing and composing those numbers in lots of different ways. We want to intentionally choose some number choices. Relational thinking does not work every single time. Sometimes you just have to solve it. But so we want to be intentional with some of those number choices and models that really reinforce looking for structure and the properties. Again, for asking students, making generalizations all the time. Is this always true? How do you know it's always true? When is there an exception? Why do you think that? There's some questions we can ask students. Is there a different problem that you've already solved? What more can you tell us about that? Oh, you were thinking about this other concept. Similar to before, is it always true? How do you know? Can you write an equivalent expression that can help you solve this? And when planning for relational thinking, we want to look at property, structure, or strategies that students are expected to use to solve. We want to ask, can students solve without calculating? You want to think about how do the operations and quantities relate? And can an equivalent representation be used to solve the problem? So we're going to do something one of my favorite strategies called the problem string. There are routines that teachers can use to help students look for and find patterns. They're very intentionally written. They're not just, numbers written one after each other. They are really focused on a particular structure or pattern. So our first one. Feel free to write in the chat the solution, what is it, and how you got it. I see most people did it exactly the way I expected, which is the best thing about creating these things is that you can sometimes predict. I said 102. I added the 330s and the 34s, and a lot of you wrote 30, 3 times 30 or 90 plus 12. Okay. Adding a little bit of sophistication here. What about this? 334 plus 334 plus 334. And by the way, you can use the problems from before in problem strings. A lot of similar things. 900 plus 90 plus 12. Or I added the 300s and the 102 from before. Hopefully I actually added it correctly. Okay, next. Parentheses, 54 plus 54 plus 54 plus 54, end parentheses, divided by 4. For this one, I'm seeing, well, there are 4 of the same numbers. So for one of them is going to be 54. Or take a 54 out. Or because there's 4 groups of 54, it has to be 54. Right, you didn't even need to solve this one. And again, I predicted what you were going to say pretty well. There are 4 54s, and 4 54s divided by 4 is a 54. What about this one? 34 plus 68, in parentheses, divided by 3. Remember to think about some patterns or other strategies we've used for the previous problems to solve this one. Oh, this is so cool. I see a lot of different strategies here. I see some people use kind of the distributive property and did 30 divided by 3, then 60 divided by 3. Some people noticed that 68 is 2 34s, so that there were 3 34s divided by 3, similar to the problem up here. Someone just said, I can see with this one I need to do more of these because I'm not as flexible as I thought. I'm still a recovering traditionalist. So one of the ways that I thought was similar. 68 is 34 plus 34. And since there are 3 34s, one of them divided by 3 would be 134. So again, using the similar pattern of thought, this is going to be our challenge one. 150 plus 27 divided by 3. What's so funny, in the chat, there is a ton of 50 plus 9, 50 plus 9, 50 plus 9. And some people write 59. But what's really funny is I asked for the solution, like one singular value for all of these. And I also wrote 50 plus 9 instead of 59. Both answers are acceptable. But I did 150 divided by 3 and 27 divided by 3 to get 50 and 9 together. Awesome. So really, this was about not only about relational thinking and equivalence, but also about MP7, right? This was intentionally designed to get y'all thinking about a specific pattern, making a generalization with these related problems. I did put a link at the bottom here, and there's a bunch of problem strings and things like that in the resources. So someone is saying, I need more of these. There are lots out there, and there's such a variety. There's books about high school algebra 2, really advanced algebra ones. So lots of resources out there. And I'm glad that you all are having fun doing these. So what is relational thinking? I'm going to reiterate again. It's the ability to reason about mathematical relationships where you don't always have to compute on either side, both sides of the equal sign. It's about patterns, it's about properties, it's about structure, and really being flexible and efficient. It goes beyond answer getting. It's really getting at understanding on how numbers and operations connect, seeing the why behind the math. And it matters because it is the foundation of algebra and advanced mathematics. It deepens our number sense and our conceptual understanding. If students are thinking relationally, they're going to know their multiplication facts better. They're going to know their addition facts better. They're going to be better at doing those operations in general. They're going to be more flexible, more efficient, and they're going to be able to provide justifications in their problem solving. And we're going to have kids talking about math and doing reasoning, which is one of my favorite things. The more people that love doing math and have fun doing it and get to talk about it, the better our world is. So before ending today, I want you to take a second and think about what is your first best next step from today's session. So pick one of do you want to choose a takeaway that you wanted to do more learning around? Maybe you want to look at Pam Weber Harris's book and investigate problem strings more. Make sure to write that down somewhere. Make sure that you know that this is the year you're going to focus on it. Maybe you want to talk about it with someone. Share it with someone from your district, or maybe just another math teacher who you think would love it, or maybe a reading teacher. I think everyone should be doing math all the time. Or set a date in your calendar when you want to really want to think about it. When's a good time? Again, the resources for all 8 sessions are here. I think the webinar will be uploaded as a link sometime, hopefully soon. I know Sarah has a crazy busy week, so we'll give her a little bit of patience.
Yeah,
go ahead.
No, it'll be uploaded today or maybe in the next week sometime. We'll see.
Yep. One of my favorite places to go is we have this one-stop doc, which you can find in this bit.ly right here. That includes this updated math calendar. This one's outdated right here, but it includes the most updated one that lists all the things that we're going to be doing. And if something gets added, we'll update that too. But this one-stop doc has everything, not just from Sarah from Standards and Instruction, but our assessment. We have stuff up there. Compass has stuff up there. If it's math in Minnesota, it's up there. So one of my favorite places to go. Frequently asked questions. Please go there. And most of all, go ahead.
Yeah, 2 tips on that. One, if you go to the second page of this document, and I'll link it in the description below if you're watching this webinar, I have put a bunch of new stuff, including something that is brand new that almost no one knows about. So you can go there and check it out, related to my webinar series last year, a resource for you. And then number 2, don't forget to Control F or Command F. You can search FAQs and all the other things.
Thank you, Sarah. And ultimately, thank you, Chimigwech. We really appreciate that you came here. Hopefully you can take something away and share it with your students. And I am so grateful that you were here and shared with us or are watching it on the internet, on YouTube. I'm just grateful. Thank you.